Currently, a device orbits over 1 million miles from our planet. It is subtly altering our understanding of the cosmos. For many years, researchers held that the universe, while immense, was ultimately quantifiable, spanning roughly 14 billion light-years in all directions. However, when the James Webb Space Telescope focused its optics on seemingly vacant blackness, that conviction crumbled. The Webb telescope uncovered galaxies emerging mere hundreds of millions of years post-Big Bang, black holes expanding more rapidly than theoretical models predict, and cosmic formations materializing much sooner than anticipated. Yet the most disquieting revelation isn't the extent of Webb's observational capability. Rather, it's the implications these discoveries hold for reality's actual magnitude and the portion of the cosmos that might perpetually remain inaccessible to us. If prepared, please press the like button, and we'll start to grasp the genuine insights the James Webb Space Telescope is providing. Initially, we must discard a common notion, the belief that space is merely something we gaze through. Within the cosmos, separation isn't solely about distance. It also represents time. Light moves at an unvarying velocity, approximately 300,000 kilometers per second. It stands as the swiftest entity known, quick enough to circumnavigate our planet over 7 times within 1 second. Nevertheless, even at such a velocity, separation instantly translates into a time lag. The instant light departs from an object, its temporal journey commences. Observing across a room means you're perceiving the past by mere billionths of a second, a lag so minuscule your mind disregards it. When viewing a far-off structure, this delay extends to millionths of a second. Yet too tiny to perceive, still inconsequential for daily existence. However, the magnitudes then start to shift. Gazing at the moon reveals it as it was 2 seconds earlier. Should the sun disappear at this very moment, its illumination would persist in reaching us for another 8 minutes from its former position. These time lags expand beyond what human instinct was developed to process. The closest star, apart from our sun, is observed by us as it existed over 4 years prior. Light from the Milky Way's core reaches us with a 26,000-year delay. Upon viewing the Andromeda Galaxy, we are witnessing photons that departed its stellar bodies approximately 2.5 million years ago. This predates documented history, the establishment of cities, and the development of language by a vast margin. The nocturnal firmament isn't a real-time depiction of existence. Instead, it serves as an archive. Each luminous point bears a chronological marker. Each individual photon acts as an envoy from a distinct period in the universe's timeline. The greater the distance that photon has traversed, the more ancient the data it conveys. However, the cosmos doesn't maintain these transmissions unaltered as it grows. Space itself undergoes expansion, meaning it's not galaxies moving outwards through space, but rather space stretching between them. This occurs subtly and without interruption, and as space expands, it elongates the light passing through it. Wavelengths become extended. High-energy blue and ultraviolet radiation transitions towards red, subsequently fading into infrared. This phenomenon is termed redshift, and it represents more than just an alteration in hue. It constitutes a tangible indicator of the extent to which the universe has enlarged since that light commenced its voyage. Redshift functions as a universal timepiece. The more elongated the light, the greater the duration it has spent in transit. Furthermore, the earlier in cosmic history it was released, the more intertwined distance and time become. Observing greater distances equates to peering further back in time. For many decades, astronomers utilized telescopes primarily optimized for visible light, the limited range of the spectrum our human eyes are capable of perceiving. Tools such as Hubble revolutionized our comprehension of proximate galaxies, nebulae, and areas where stars are born. These instruments uncovered movement, configurations, and remarkable intricacies. However, as researchers extended their observations further into the past, the cosmos appeared to become less dense. The reason wasn't its absence, but rather that its light had undergone a transformation. As illumination from the most ancient galaxies traversed the expanding cosmos, it became elongated past the visible spectrum. Upon its arrival at Earth, a significant portion of this light was no longer detectable by the range these telescopes were built to observe. Vast areas of the nascent universe grew challenging to discern. The apparent darkness was not devoid of matter. It was indecipherable. The James Webb Space Telescope was constructed to interpret what previous instruments were incapable of. From its inception, Webb was designed specifically for infrared light. Its primary mirror measures over 6 meters across and is covered by a microscopically thin layer of gold, selected due to its exceptional capacity to reflect infrared wavelengths with remarkable efficiency. It does not circle Earth. Instead, it functions almost 1 million miles distant at a gravitationally stable point, allowing it to stay constant and unperturbed. This separation is crucial. For Webb to detect subtle infrared signals, it needs to maintain an exceptionally low temperature. Infrared light is intrinsically linked with heat, and a warm telescope would emit light in the very same wavelengths it endeavors to observe. This would obscure the cosmos's most subtle signals. Webb needed to become sufficiently silent to perceive. A colossal sun shield prevents thermal energy and illumination from the sun, earth, and moon. On its unilluminated face, the telescope cools to temperatures at which ancient photons can be discernible amidst the gloom. Only under these conditions can Webb perceive light that has journeyed for billions of years. When Webb gazes upon a region of sky that looks utterly dark to our vision, it is not seeking emptiness. It is patiently awaiting, anticipating photons that commenced their voyage when the cosmos was in its infancy. Photons elongated nearly to the point of imperceptibility by the very expansion of space. These photons do not come in torrents, they arrive gradually, occasionally individually. Webb might observe the same celestial area for numerous hours, even days, assiduously gathering illumination that traversed almost the entirety of the observable universe. And what it discovers there is not a tranquil genesis, rather, it uncovers activity. Galaxies emerge in unforeseen locations, systems already generating stellar bodies, structures already coalescing. The nascent universe does not seem hesitant or delicate, it appears bustling. There is something profoundly awe-inspiring about this endeavor. Webb does not record pictures in the conventional manner. Instead, each image constitutes a mosaic constructed from ancient journeys. Each photon within the frame departed its origin point long before Earth came into being. Ages before the sun flared to life, eons before the Milky Way assumed its current configuration, every chapter of human history transpired while that light was already en route. By the time Webb perceives it, we are not observing current occurrences. We are instead witnessing moments that transpired eons ago, maintained during their journey. These cannot be re-examined. They cannot be modified. This is the reason astronomers assert that James Webb does not merely gaze into the distance. It peers backward through the annals of time. Distance serves as a chronological record. Proximate objects depict the cosmos nearer to the current era, whereas remote objects unveil progressively earlier stages of cosmic history, superimposed one behind the other. Nevertheless, even Webb's remarkable observational capability possesses a boundary. No telescope is able to perceive past a limit established by physics itself. The extent of light's journey since the cosmos originated establishes this limit. This region is referred to as the observable universe. This isn't a spatial limit, but rather a limit to what we can know. Past this frontier, space persists, galaxies endure, stars are born and perish, and black holes coalesce. Complete cosmic narratives perpetually unfold beyond our grasp, not due to technological constraints, but because the expansion of space itself prevents their light from ever reaching us. The James Webb Telescope hasn't uncovered the ultimate boundary of existence. Instead, it has shown us the vast extent of reality that remains forever unobservable to us. As the Webb telescope approaches this frontier, identifying galaxies that are earlier, more luminous, and more abundant than anticipated, a profound understanding starts to emerge. Should the cosmos already be so abundant, at the very edge of our perception, then the actual magnitude of all that exists must vastly exceed our previous conceptions. In a significant portion of contemporary cosmology, the nascent universe was envisioned as constrained, not void, but tranquil. Following the Big Bang, space expanded, temperatures decreased, and matter dispersed nearly uniformly in all directions, leaving behind only minor inconsistencies. Within this framework, gravity was presumed to operate with patience. Gas required a period to cool, and dark matter halos needed sufficient time to expand enough to ensnare conventional matter. The formation of stars demanded millions of years. Galaxies, upon their eventual emergence, were anticipated to be diminutive and dim, delicate structures that would necessitate hundreds of millions of years to evolve into anything significant. This anticipation influenced theoretical frameworks for decades, leading astronomers, when the James Webb Space Telescope commenced its observations of the early universe, to foresee scarcity rather than profusion. They envisioned a few rudimentary galaxies dispersed across a largely dark cosmos, systems barely cohesive, a universe still establishing its fundamental structure. Conversely, Webb discovered multitudes. Luminous galaxies repeatedly emerged during epochs that ought to have been largely vacant. These were not faint glimmers barely surviving. They were already dynamic, already organized, and already generating stars at vigorous paces. The astonishing revelation wasn't an isolated, peculiar entity. Rather, it was the recurring trend. An excessive number of them existed within the initial 500 million years of the universe. Webb observed galaxies emitting vast quantities of light. Certain ones encompassed hundreds of millions, or even billions, of solar masses and stars. Based on established models, accumulating such a quantity of material ought to have required considerably more time than the universe had at its disposal. While gravity possesses immense strength, it operates slowly. Gas doesn't undergo immediate collapse. It needs to shed energy and cool dark matter. Halos are required to expand via mergers and accumulation. Stars must come into being, consume their fuel, and ultimately cease to exist. Every stage dictates a time frame that cannot be bypassed. Nevertheless, the galaxies were already present. What rendered this even more disquieting was not merely their luminosity or bulk, but their advanced chemical composition. Webb identified traces of elements such as carbon, oxygen, and nitrogen within some of these nascent galaxies. These particular elements did not originate from the Big Bang. Instead, they were synthesized within stars, which only released them upon their demise. Their existence implied an undeniable fact. A minimum of one prior stellar generation must have already emerged, existed, and concluded its lifespan, all within the initial few hundred million years of the cosmos. The timeline of the universe appeared to be accelerated. To grasp the profound concern this caused astronomers, it's beneficial to consider it in relatable concepts. Constructing a galaxy isn't a solitary action, it's a progression. One cannot erect skyscrapers prior to the existence of roads. Similarly, concrete cannot be poured before steel has been manufactured. Every phase relies upon its predecessor. The nascent universe was presumed to be in the process of establishing its groundwork. Webb, however, discovered structures already established. This increasing discrepancy between theoretical forecasts and empirical findings became recognized as the too much light, too early conundrum when scientists computed the expected total light output from galaxies during the universe's initial billion years. Their projections proved insufficient, occasionally by multiples of 2, 5, or even greater. This represents a clear indication, not merely a minor calculation discrepancy. Researchers reacted as is customary. They scrutinized the measurements, recalibrated the equipment, and investigated if cosmic dust might be causing galaxies to seem more luminous than their actual state. Furthermore, they assessed whether gravitational lensing was amplifying remote systems, or if presumptions about stellar populations were inflating mass calculations. Repeatedly, the finding remained consistent. The primordial cosmos was not faint, rather, it was luminous. Certain galaxies detected by Webb were so immense that scientists temporarily dubbed them universe breakers. These were entities whose presence appeared to challenge the very boundaries of cosmology, given that, according to conventional models, galaxies of such magnitude should not have existed during those nascent epochs. Initially, there was an expectation that their masses had been overestimated. It was hypothesized that the illumination wasn't solely originating from stars. Perhaps actively feeding black holes were contributing additional brightness, thereby making galaxies appear more expansive than their true size. Subsequent analysis indicated this provided some assistance. However, this was only a partial explanation. Indeed, a number of nascent galaxies contain potent black holes. Factoring in their contribution mitigated the most extreme instances. Nevertheless, even following those adjustments, the primordial cosmos still harbored approximately twice as many massive galaxies as theoretical models had predicted. The discrepancy diminished, yet it did not vanish entirely. Webb subsequently replicated these observations across diverse celestial regions, employing varied instruments and wavelengths. Consistently, the identical pattern manifested. The primordial cosmos was densely populated, stellar genesis was highly effective, and structures materialized swiftly. This compelled astronomers to reevaluate a fundamental premise. What was the efficiency with which the universe could convert gas into stars? Within the contemporary universe, the process of stellar formation is remarkably inefficient. The majority of gas inside galaxies never transforms into stars. Instead, it is heated, agitated by turbulence, dispersed by radiation, or disrupted by stellar outflows, allowing only a tiny proportion to condense into nascent suns. Nascent galaxies appear to have operated under distinct circumstances. One potential factor is density. The primordial universe occupied less space, matter was compressed more tightly together, and gaseous clouds experienced more frequent collisions. Composition presents a further possibility. The initial generations of stars arose from almost pure hydrogen and helium, lacking heavier elements that would complicate their cooling. Galactic mergers likely played a role as well. In the nascent universe, galaxies were in closer proximity, collisions occurred frequently, and when galaxies coalesce, gas is propelled inward and compacted to extreme densities, triggering powerful episodes of stellar genesis. While each of these concepts elucidates a portion of the overall scenario, none offers a complete resolution. A further enigma resides at the cores of numerous nascent galaxies. Webb has identified supermassive black holes that were already established when the cosmos was less than 500 million years old. Some possess masses millions or even billions of times greater than that of our Sun. As per conventional theoretical frameworks, such an occurrence ought to be impossible. Black holes originate from the collapse of stars, yielding entities merely tens of solar masses in dimension. Although they can expand by accreting ambient material, their growth is constrained by the energy emitted. Even as matter accretes, Webb continues to detect them. This has compelled astronomers to contemplate scenarios previously deemed radical. The direct collapse of colossal gaseous clouds, primordial stars significantly more massive than contemporary ones. Swift coalescences within a compact, nascent cosmos. No single one of these hypotheses has been substantiated, nor can any currently be dismissed. The significance of this epoch stems from the fact that these nascent galaxies profoundly influenced all subsequent developments. Their emitted radiation fundamentally altered the cosmos. Their supernovae dispersed heavy elements throughout space. Gravitational forces then shaped the initial large-scale structures. Should their formation have occurred sooner and more rapidly than anticipated, the whole chronology of cosmic development would be altered. With Webb's ongoing exploration further back in time, this trend is increasingly difficult to disregard. The cosmos wasted no time. It rapidly formed stars, galaxies, and black holes at a speed that defies our current calculations. This demonstrated that the nascent universe did not have a delicate genesis. Instead, it was characterized by a burst of activity, a perspective held throughout much of the 20th century. Astronomers believed they had reached a satisfactory response to one of the most profound questions conceivable. What is the total number of galaxies in the cosmos? The approach was conceptually straightforward, though challenging to execute. Direct a potent telescope towards a small, apparently vacant area of the sky and tally all discernible galaxies. Subsequently, extrapolate that figure to estimate the total for the observable universe. The outcome was astounding when the Hubble Space Telescope conducted its most profound observations. Within a celestial area no bigger than a grain of sand viewed at arm's length, Hubble uncovered almost 10,000 galaxies. Back then, the image seemed immense. Based on this, scientists calculated that the cosmos held several hundred billion galaxies. This figure was nearly unfathomable, and it remained unchallenged for many years. Subsequently, the James Webb Space Telescope examined the identical dark regions where previous photographs had indicated voids. Webb revealed structure. Where dark voids previously divided distant blurs, Webb discerned subtle infrared emissions, multiple strata of galaxies positioned one behind the other. Their concealment was due not solely to distance but to wavelength. This represented not a flaw in previous telescopes, but rather a boundary of their observational capability. With the expansion of the cosmos, radiation from far-off galaxies elongates into extended wavelengths. By the point this light arrives at Earth, a significant portion of it is no longer within the visible spectrum. Those telescopes were built for a different kind of observation. The galaxies had always existed. Their emitted light had merely moved beyond detection. Webb was constructed specifically to track it. During one of its most challenging deep-field surveys, Webb concentrated on a celestial area just marginally bigger than 3 full moons. Over hundreds of hours, positioned side by side, it gathered thousands of distinct exposures. It meticulously collected weak infrared signals that had journeyed for eons. Upon the amalgamation of these images, the outcome proved astonishing. Almost 800,000 individual galaxies occupied the view. This many galaxies in a section of the heavens that most individuals would characterize as devoid of content. To grasp the magnitude of this finding, envision reproducing the renowned Hubble ultra-deep field on one sheet of paper. For Webb's image to be shown with an equivalent level of detail, the print would have to exceed 13 feet in height and 13 feet in width. This represents a mural-sized depiction of universal history. Furthermore, each luminous point within that picture is not a star, but rather a galaxy. Within each of these galaxies reside millions, billions, and occasionally trillions of stars. A considerable number of them harbor planetary systems. A multitude possess abundant dust and heavy elements created through countless cycles of stars forming and dying. The cosmos is not thinly scattered with solitary celestial bodies floating in obscurity. Instead, it is tightly concentrated. The remarkable aspect of this finding is that the Webb telescope did more than just enumerate galaxies. It took measurements for every single one. For every individual galaxy, scientists are able to determine its distance, mass, rate of star creation, and approximate age. Collectively, these measurements enable researchers to piece together the evolutionary path of galaxies throughout almost the entire existence of the cosmos. Upon doing so, a more profound arrangement became apparent. Galaxies do not disperse haphazardly across the cosmos. Rather, they gather together and arrange themselves. They delineate unseen routes, spanning immense distances. When viewed on the grandest scales, the cosmos appears akin to an expansive cosmic network. Extended strands of material, extending for tens and hundreds of millions of light years, converge at concentrated points where groupings of galaxies originate. These are interspersed with enormous areas containing virtually no matter. This particular arrangement had been theorized for many decades. The Webb telescope brought it into sharp focus. A significant number of the galaxies observed by Webb were obscured by cosmic dust, which obstructs visible light yet permits infrared radiation to penetrate. Whole groups of dusty, star-producing galaxies are now visible for the first time, occupying voids where previous observations found nothing, and finishing configurations that previously seemed incomplete. This is significant because the arrangement of galaxies is not merely ornamental. It serves as a historical record from the period following the Big Bang. Material was distributed nearly uniformly throughout space, featuring minute density fluctuations established during the cosmos's initial stages. Areas possessing marginally greater density exerted a marginally more potent gravitational pull. Gradually, matter gravitated towards these areas, thereby intensifying the disparities. Gravitational forces sculpted space into thread-like structures and junctions, drawing material away from adjacent zones and creating immense empty spaces. A helpful comparison can be made with precipitation. On irregular landscapes, water courses into depressions, forming streams and rivers, whereas elevated areas remain arid. Eventually, an organized topography develops. The cosmos underwent development in a very similar fashion. The sole difference was that the moving material was matter itself. Data from Webb indicates that this phenomenon commenced at an early stage. Strands extending for tens of millions of light-years were already present when the cosmos was merely a few billion years old. Certain formations were so vast and well-ordered that they defied predictions regarding the speed at which matter could self-organize. A particularly notable instance is a formation scientists have named the cosmic vine, which is a sequence of over 20 densely grouped galaxies spanning more than 13 million light-years. These galaxies were present during the universe's early period, yet this arrangement competes in size with considerably more ancient structures. What renders this configuration particularly fascinating is its current condition. Multiple of its most massive galaxies have ceased producing stars, having either depleted or shed the requisite gas for new stellar generation. Such an occurrence is uncommon at such an early juncture in cosmic evolution. The underlying meaning is nuanced. Surroundings play a crucial role. Galaxies situated in concentrated areas develop distinctly from those existing in isolation. Mutual interactions and fusions hasten their developmental stages. Expansion occurs swiftly, resources are used up quickly, and this phenomenon is not uncommon. Astronomers utilized Webb's data to compile the most extensive catalog of galaxy groups ever created, comprising over 16 groups and protoclusters that range from approximately 12 billion years in the past to merely a few billion years ago. These collections serve as the foundational components for the enormous galaxy clusters we observe today. Scientists are able to observe the progression of structure formation throughout time by contrasting groups located at varying distances. Initial groups exhibit a disorganized appearance, characterized by vigorous star formation. Subsequent groups demonstrate a growing degree of organization, displaying more uniform shapes, and a decelerated rate of expansion as gravitational forces assert dominance. Such an uninterrupted perspective spanning billions of years remained unattainable prior to Webb. Nevertheless, despite all this compactness and arrangement, the cosmos is simultaneously characterized by its vast void. Immense empty spaces exist amidst the filaments of the cosmic web. These are areas extending tens to hundreds of millions of light-years wide, holding an extremely sparse number of galaxies. Far from being minor gaps, these voids constitute the most expansive structures in the cosmos when measured by volume. Should one be positioned at the core of such a void and gaze in any direction, only darkness would be visible, extending for tens of millions of light-years prior to spotting the closest galaxy. Whole areas of space did not accumulate matter, solely due to gravity drawing that material to other locations. Webb's deep field photographs strikingly illustrate this stark difference. Compact groupings of galaxies are visible next to expansive dark areas that hold virtually no content whatsoever. The cosmos is simultaneously populous and vacant, leading us back to statistical figures. Assuming Webb's deep fields accurately represent the universe and various directional observations support this, then the overall count of galaxies within the observable cosmos might not be in the hundreds of billions, but rather in the trillions. For each galaxy previously thought to exist, numerous others could be concealed beyond the scope of prior investigations. An increased number of galaxies implies a greater quantity of stars, which in turn suggests more planets, thereby transforming the universe into something not merely vaster in dimension, but also more abundant in potential. However, even this phenomenon is confined solely to the observable universe. Outside of its boundaries, space persists. Structure endures. Galaxies persist. Consequently, if reality within our visible segment is so densely packed, then the actual magnitude of all that lies beyond it cannot possibly be overlooked. Initially, the universe appears straightforward to quantify. The Big Bang event occurred approximately 13.8 billion years in the past. Given that light moves at a constant velocity, it seems logical to presume that the farthest objects discernible to us would be roughly 13.8 billion light-years distant. This assumption is incorrect. The observable cosmos does not possess a radius of 13.8 billion light-years. Its radius measures approximately 46.5 billion light-years, resulting in a diameter of nearly 93 billion light-years. This finding is neither conjecture nor overstatement. It represents an empirically determined outcome substantiated by observations of the universe's expansion and the characteristics of primordial light. The perceived impossibility stems from its conflict with our innate understanding of movement. No entity is capable of traversing space at a speed greater than that of light. That principle remains valid. No galaxy is accelerating away at inconceivable velocities, nor is any signal violating a universal speed restriction. Rather, the cosmos expands in a more subtle and considerably more peculiar manner. It elongates space itself. When distant galaxies are described as receding from us, one might be inclined to visualize them hurtling outwards akin to debris from an explosion. This mental picture is profoundly inaccurate at grander scales. Galaxies are not, in fact, traversing through space whatsoever. Instead, they are being separated as the intervening space itself undergoes expansion. A straightforward comparison aids in clarifying this concept. Visualize points marked on the surface of a balloon. As the balloon inflates, each point moves further away from every other point. This occurs not because the dots are gliding across the surface, but rather because the surface itself is stretching. No dot occupies the center, nor is any dot unique. The cosmos operates in a very similar fashion. A remote galaxy, when it released the light we perceive currently, was considerably nearer to us than its present location. For billions of years, as that light journeyed towards Earth, the expanse separating us and the galaxy steadily grew. By the moment the light reached us, the galaxy from which it originated had been propelled tens of billions of light-years further off. This explains our ability to see galaxies whose light has been en route for over 13 billion years, despite their present separation exceeding 46 billion light-years. Light does not traverse a static distance. Instead, it progresses through a span that expands during its journey. Essentially, light is operating on a universal treadmill. During the early stages of the cosmos, expansion proceeded at a slower pace, allowing light to advance consistently. With the passage of time, the expansion quickened, elongating distances at an increasing rate. Certain photons succeeded in reaching us because they commenced their voyage sufficiently early. Other photons will never arrive. This establishes a limit, not a physical barrier or an extremity. It constitutes a horizon, specifically the cosmic horizon. This denotes the maximum extent of what can ever be perceived from our vantage point, considering the universe's finite age and how space expands beyond this boundary. Light fails to reach us not due to a lack of time. Rather, it's because the expanse it needs to cover expands more rapidly than light can cross it, and this is precisely where the cosmos turns profoundly disquieting. Space does not terminate at the cosmic horizon. Our understanding stems from the fact that the universe appears fundamentally identical in all directions we survey. The quantity of galaxies does not diminish towards a periphery, and the cosmic microwave background, which is the faint residual glow from the Big Bang, presents itself as almost consistent throughout the whole sky. Such uniformity would be unattainable if space were to cease suddenly just past our line of sight. Therefore, the universe stretches beyond our visual range, yet it does so in a manner that perpetually conceals a significant portion of itself. Past 4.6 billion light-years, galaxies persist, stars continue their cycles of birth and demise, black holes keep merging, and complete cosmic narratives develop in areas that will never affect us and can never be affected by us. No transmission from those areas will ever arrive on Earth. not due to insufficient technology, but because space-time itself precludes it. What's even more disquieting is that this demarcation isn't static. With the progression of time, the observable cosmos expands as light originating from more remote areas has had an extended duration to reach us. The boundary gradually extends outwards. Concurrently, the universe's expansion is quickening, leading space to distend more rapidly now compared to previous times. These dual phenomena contend. The outcome is a cosmos where certain entities become visible for a short period, only to subsequently vanish from our grasp permanently. Galaxies currently within our sight are not assured to stay observable. Their emitted light persists in stretching. As their light shifts to longer wavelengths, growing fainter and more dispersed over time, those galaxies, from our viewpoint, seem suspended at a specific point in their evolution. They gradually dim and ultimately vanish. This isn't some far-off theoretical concept. It stems directly from the observed rates of expansion. Should the universe maintain its current behavior, then in approximately 100 billion years, every galaxy beyond our local gravitationally linked cluster will pass beyond the cosmic horizon. Observers in the future would perceive a cosmos comprising merely a small grouping of proximate galaxies enveloped by obscurity. They might never become aware that anything else had ever come into being. This alters the very definition of observation. The observable cosmos is not the entirety of the universe. Rather, it represents the segment of the universe that is perceivable from our current position in cosmic time. If one were to relocate to a different galaxy, the observable cosmos would shift. New areas would become visible, concurrently with others receding past the cosmic horizon. Each spatial position establishes its unique observable sphere. This phenomenon results in peculiar circumstances. It's possible for two galaxies to be discernible from Earth, but mutually invisible to one another. Their positions might be on opposing sides of our cosmic boundary. While light from both sources arrives at our location, the light from one can never reach the other. From their respective viewpoints, Earth itself could be situated beyond their own cosmic limits. No single vantage point is superior, no central location exists, and no position allows for a complete view of the cosmos. Each observer is positioned at the core of their individual observable universe. This underscores the importance of venturing further into space. Through the detection of galaxies nearer to the cosmic boundary than previously achieved, observation compels us to face the ultimate boundaries of knowledge itself. The distant galaxies we observe are no longer in the positions where their emitted light originated. Their subsequent development, their fusions, and their ultimate destiny remain beyond our comprehension as that data continues its journey through the cosmos. Distorted by cosmic expansion and often destined never to reach us, our perception is not of the present reality. It represents the past, and even that historical glimpse is partial. Past the visible boundary resides the unobservable cosmos. This encompasses areas potentially holding galaxies, clusters, and formations equally as intricate and abundant as those within our sight. Certain theoretical frameworks propose an infinite universe, while others posit it is finite yet immeasurably immense. Regardless, the portion of the universe we can observe is nearly certainly merely a segment of its entirety. The James Webb Telescope has not uncovered the universe's boundary. Rather, it has demonstrated the absence of any reachable edge whatsoever. As this understanding takes hold, a further inquiry becomes inescapable. Should cosmic expansion obscure such a significant portion of reality, then some force must be propelling it. To grasp this accelerating power, we are compelled to address the most prevalent and enigmatic component within the cosmos itself. Throughout much of the 20th century, the narrative of the universe appeared consistent. The Big Bang initiated all motion. Space broadened and gravity gradually exerted its influence, attempting to decelerate that expansion. The primary discussion centered not on gravity's significance, but on the ultimate conclusion of the cosmic narrative. Would the universe continue its expansion indefinitely? Alternatively, would gravitational forces ultimately recoalesce all matter? Each iteration of that discussion operated under the identical premise: gravity held sway. That premise failed to withstand empirical scrutiny. During the latter part of the 1990s, astronomers were examining remote stellar detonations referred to as Type 1a supernovae. These stellar outbursts exhibit almost uniform luminosity upon each occurrence, establishing them as dependable cosmic distance indicators. By assessing a supernova's apparent brilliance, contrasting it with its expected brightness, the disparity indicates its remoteness. When that distance is combined with the recession velocity of its parent galaxy, the universe's expansion timeline becomes clear. The findings from those measurements were unequivocal. The cosmos was not decelerating. Instead, it was accelerating. Remote galaxies were situated at greater distances than anticipated if gravity were progressively moderating the expansion. The more extensively astronomers observed, the more distinct the trend emerged. Expansion had not simply persisted, it had been gaining speed for eons. An unknown force was propelling space outwards. To explain this phenomenon, the field of cosmology found it necessary to propose a novel component: dark energy. Dark energy neither emits nor absorbs light, nor does it coalesce into stars, planets, or galaxies. Consequently, we cannot directly observe it. Its existence is inferred from its impact on space itself, an effect that predominates throughout the universe. According to measurements, dark energy constitutes approximately 68% of all existing entities. What we commonly refer to as ordinary matter encompasses everything familiar to us. This comprises less than 5% of the total. Dark matter makes up the majority of the remainder. The observable cosmos represents only a minor segment of reality. The particularly disquieting aspect of dark energy lies in its conduct during the universe's expansion. As space expands, the concentration of normal matter diminishes. If the volume of space doubles, matter's density is reduced by half. Electromagnetic radiation dissipates at an even quicker rate. Dark energy, however, deviates from this principle. Its concentration stays uniform even while the cosmos expands. With the enlargement of space, the overall quantity of dark energy grows. A self-reinforcing cycle is thus established. Increased space generates additional dark energy, which in turn propels accelerated expansion, thereby creating even more space. Across eons, this subtle cycle altered the cosmic power dynamic. In its nascent stages, matter held sway, permitting gravity to fashion galaxies and clusters within the cosmic web. However, as cosmic expansion attenuated matter, dark energy assumed control approximately 5 billion years ago, becoming the primary driver of the universe's expansion. While the James Webb Space Telescope cannot directly observe dark energy, its telltale signs are ubiquitous. Webb identifies these signs in the significant redshift of primordial light, the vast scale of the observable cosmos, and the recession and dimming of remote galaxies. Dark energy's impact is discernible throughout the heavens. Were it not for dark energy, the cosmos would be considerably more compact. The cosmic boundary would be significantly nearer, and extensive areas of space currently within our observational reach would have remained unseen. Dark energy's role extends beyond merely influencing the present. It also dictates the future. Should dark energy maintain a constant value, as indicated by present observations, the universe's expansion will persist indefinitely. Gravitational forces will continue to bind galaxy clusters, yet all entities beyond them will gradually recede. In trillions of years, as objects individually cross the cosmic horizon, observers within a galaxy such as the Milky Way would perceive a cosmos populated solely by proximate stars and little else. The cosmos would persist, yet it would seem nearly devoid of content. This scenario, however, is made more intricate by one of contemporary cosmology's most profound outstanding issues. This issue, which the James Webb Telescope was anticipated to alleviate, has instead been exacerbated by it. When astronomers quantify the current rate of cosmic expansion, they obtain not one but two distinct values. One approach involves examining the distant past through the cosmic microwave background, which is the faint residual radiation emitted when the universe was merely around 380,000 years old. Scientists deduce an expansion rate of roughly kilometers per second per megaparsec from the delicate structures within that radiation. The alternative technique focuses on closer observations. By employing Cepheid variable stars and type Ia supernovae to gauge galactic distances, astronomers subsequently correlate these measurements with the galaxy's recession velocities. This methodology consistently yields a greater figure, approximately 73 kilometers per second per megaparsec. The two measurements are accurate. Each has undergone multiple repetitions and thorough examination. However, they are inconsistent. This divergence is termed the Hubble tension, signifying a significant flaw in our cosmic comprehension. The James Webb Telescope was anticipated to settle this issue. Through improved distance calculations, Webb validated the accelerated expansion rate. The tension persisted, growing increasingly difficult to disregard. This presents cosmology with challenging scenarios. Perhaps an undetected error exists within the measurements, or our fundamental cosmic assumptions are flawed, or entirely new physics awaits discovery. A potential explanation is that dark energy's power isn't truly fixed, but rather fluctuates across cosmic epochs. Alternatively, the early cosmos might have functioned unlike our current models, leaving behind expansion signatures still observable. Every one of these possibilities holds significant ramifications. The rate of expansion dictates the universe's age, its overall dimensions, and its eventual destiny. Should our comprehension be flawed, numerous conclusions reached over many decades might require reevaluation. Furthermore, a more drastic outcome remains a possibility. Should dark energy intensify rather than maintain its stability, cosmic expansion might ultimately overcome gravitational forces, even locally. This would lead to the disintegration of galaxy clusters, and in severe instances, galaxies themselves would dissipate. In a far-off future, even atoms might be ripped asunder, a phenomenon occasionally referred to as the Big Rip. While present data doesn't support this conclusion, a degree of doubt persists. It is already evident that dark energy holds sway over the universe. It expands space-time and conceals immense portions of existence from our perception. It dictates what future observers can perceive and what will forever remain unknown to them. This is why the observable universe extends across 93 billion light-years, and it's the cause for the majority of reality being perpetually beyond our grasp. Nevertheless, dark energy by itself fails to account for the universe as we perceive it. For while it expands space on grander scales, another force must coalesce matter on more localized ones. Something must enable galaxies to materialize rather than dissipate into a homogeneous void. This force, too, is imperceptible, equally enigmatic, and equally crucial for comprehending how the cosmos constructs its architecture, even amidst its expansion. Our focus must shift to the hidden scaffolding that binds all things. While dark energy dictates cosmic expansion, dark matter conversely dictates its cohesion. Lacking it, the universe observed by the James Webb Space Telescope would be utterly unrecognizable. Galaxies would never have formed, clusters would have scattered, and no large-scale cosmic architecture would have materialized. Dark matter neither radiates light nor absorbs it, nor does it emit any detectable radiation. Despite this, it constitutes over 5 times the mass of all visible matter. Approximately 85% of the universe's total matter content is dark matter. Each star, every galaxy, and every luminous nebula resides within a scaffold, primarily composed of something inherently unseen. What becomes visible to us isn't the underlying structure itself, but rather the lit exterior of a far more profound design. Initial indications of dark matter emerged almost 100 years prior. Astronomers observed galaxies exhibiting behaviors that contradicted predictions. Stars situated in the peripheral areas of spiral galaxies. Their orbital velocities were excessively high, moving at speeds that ought to have ejected them into the void between galaxies if only visible matter were present. Rather than escaping, they stayed tethered, moving as though every galaxy was encased within a vast, invisible halo of mass. This hidden mass was dark matter. With the expansion of observations, the corroboration increased. Whole galaxy clusters exhibited this identical issue on significantly grander scales, as individual galaxies move too rapidly to be solely contained by stars and gas. Gravitational lensing brought to light distortions in distant galaxies that visible matter could not account for. The repeated observation of light bending in regions where little to nothing was discernible made the conclusion inescapable. The majority of the universe's matter is unseen. Dark matter's significance stems not merely from its abundance, but also from its conduct. Unlike conventional matter, dark matter neither impacts itself nor dissipates energy by emitting radiation, which allows it to traverse space almost without friction. Dark matter started aggregating exceptionally early, soon after the Big Bang. The cosmos was largely homogeneous, bearing minute density fluctuations impressed during its initial phases. Dark matter reacted initially, silently collecting into expanding concentrations, whereas ordinary matter stayed heated and resisted collapsing. These accumulations evolved into immense halos, unseen, controlling, and pervasive. With the universe's cooling, conventional matter started descending into these dark matter gravitational traps. Gas accumulated and compressed due to gravity, temperatures ascended, nuclear fusion commenced, giving birth to the inaugural stars. Eventually, those stars coalesced into galaxies, not by chance, but precisely in locations where dark matter had already sculpted the environment. The observable universe mirrors an unseen design. This mechanism gave rise to one of reality's most remarkable characteristics, the cosmic web at its grandest scales. Matter is organized into immense filaments spanning tens to hundreds of millions of light-years, converging at dense junctions where galaxy clusters emerge and demarcated by colossal voids where virtually nothing resides. This arrangement is not accidental. It represents gravity in action. James Webb's observations have rendered this architecture with greater clarity. Through cataloging hundreds of thousands of galaxies and ascertaining their distances, astronomers are able to chart matter's distribution across space and time, uncovering patterns previously confined to theory. The configuration is undeniable. Galaxies arrange themselves along filaments, congregate at intersections, and steer clear of expansive empty zones, adhering to an unseen framework that molds all we perceive. Webb's capacity to penetrate dust and discern dim, remote galaxies completes the information missing from prior surveys. It demonstrates the early emergence of these structures, indicating that filaments were already firmly in place when the universe was merely a few billion years old. Matter traverses these filaments, not in a figurative sense, but physically. Gas courses through space akin to vehicles on cosmic thoroughfares, nourishing galaxies and facilitating their expansion. Galaxies do not develop independently. They are linked, provisioned, and directed by routes established by dark matter itself. Our own galaxy, too, takes part in this phenomenon. The Milky Way navigates through space, following paths sculpted by unseen mass. Its movement is directed by gravitational forces instead of randomness. For many decades, the cosmic web primarily resided in simulations, deduced from theoretical models and circumstantial proof. This situation recently altered. Employing gravitational lensing, astronomers directly identified dark matter along the filaments themselves. Through measuring subtle distortions in the illumination from remote background galaxies, they uncovered mass that no visible matter could explain. Dark matter was not restricted solely to clusters. It extended throughout space, weaving the universe into a cohesive whole. This converted the cosmic web from a conceptual model into an empirically observed structure. The universe is not merely a scattered assortment of galaxies drifting away. It is an interconnected system molded and maintained by unseen matter. Galaxy clusters, the most massive gravitationally bound entities known, are situated at the most concentrated junctions of this network. These clusters function as anchors, drawing matter along filaments towards their cores and altering galaxies as they descend inward. Gas gets removed, the creation of stars decelerates or ceases. Configurations are modified. James Webb has documented galaxies undergoing these very transformations, illustrating how their surroundings influence cosmic development. The cosmic web is far from stationary. It is vibrant, ever-changing, and perpetually developing. Yet even with its significant impact, dark matter continues to be among the most profound enigmas in the realm of physics. Its composition remains unknown to us, whether it comprises undiscovered particles or entirely novel types of substance. Furthermore, even after many decades of research, it has never been directly observed within a laboratory setting. Nevertheless, its existence cannot be disputed. If dark matter were to be excluded from calculations, the cosmos as we perceive it would be unable to form. No galaxies would ever take shape, nor would any cosmic structure materialize, and the universe would persist as an almost featureless haze. While the James Webb Space Telescope does not resolve the enigma of dark matter, it does underscore its pivotal function by demonstrating the rapid formation of structure in the nascent universe. The Webb telescope illustrates that ordinary visible matter by itself would have been insufficient for this task. Dark matter supplied the initial impetus. This accounts for the present-day appearance of the universe, including the immense emptiness of cosmic voids, the concentrated abundance of galaxy clusters, and the thread-like structures linking them as if they were celestial spans. However, this unseen scaffolding functions within a cosmos that is simultaneously being stretched apart by dark energy. Cosmic architecture is constructed by dark matter while dark energy expands space. The cosmos maintains a perpetual state of opposition between these two imperceptible powers. At more confined dimensions, gravitational pull dominates, enabling the formation of galaxies and the expansion of clusters. Conversely, across vaster expanses, cosmic expansion takes precedence, propelling areas of space beyond all observable limits. The James Webb Space Telescope has revealed that the universe is not just vaster than anticipated, but also more structured and intricately linked. Moreover, it relies more heavily on unseen energies than previously conceived. The visible elements, stars, galaxies, and luminous nebulae, represent merely the illuminated exterior. An invisible underlying structure exists beneath this surface. Furthermore, this immense and interwoven cosmos constitutes only the portion accessible to our observation. From our specific vantage point in space-time, the universe extends further still.